This video presents the progress of Replicate project at its first milestone in month 18. The Replicate pipeline helps users to 3D scan objects or friends with a generic smartphone. Users point their smartphones at the target and move around it to capture visual details. The smartphone automatically selects keyframes that are then sent to a 3D reconstruction cloud service. This service uses a progressive reconstruction algorithm to generate a sparse point cloud, which are triangulated from the keyframes. After sparse point cloud creation, a densification process increases the number of triangulated points. Dense point clouds are cleaned semi-automatically, removing background noise from incorrectly triangulated points. An object mesh is generated from the cleaned dense point cloud. Artifacts from the meshing, like holes or surface deformations, are corrected semi-automatically. The mesh is then textured to give a realistic appearance to the 3D model. Finally, the best mesh polygons are selected to produce an optimized 3D model. The 3D model is stored in a database for future user access. 3D models can be used in creative applications such as virtual reality, 360-degree videos and augmented reality. The Replicate acquisition process involves a frame selection application, and something to replicate, for example, a handy friend. The user moves around the object and the application automatically selects the best keyframes. The application user interface shows the most recent selected keyframe, together with the current 3D reconstructed model. The selected keyframes are sent to the cloud server, while the model is periodically updated from the cloud. The cloud server is composed of a front end to allow the user to browse the selected keyframes, and a back end that performs structure from motion on the frames. The user can then view the 3D reconstructed model in the form of a sparse point cloud. The front end has several options, which include the visualization of the final dense point cloud, the dense point cloud can be semi-automatically edited. Outliers are automatically detected based on their position and color. These outliers can then be deleted. A second editing step allows the user to manually select parts of the point cloud and to delete them. The dense point cloud can now be used to generate the mesh. The meshing process uses the normals, computed during the structure from motion. The cloud server automatically generates the mesh using the Poisson approach. At this stage, the colors of the mesh are directly computed from the colors of the dense point cloud. The mesh cleaning process is performed semi-automatically. Unwanted parts of the mesh can be precisely selected and deleted. The editing tool allows the user to zoom in and refine the cleaning. Larger portions of the mesh can be deleted too. Holes generated by the deletion of mesh parts are automatically filled through mesh interpolation. After the mesh has been cleaned and polished, it is ready to be textured. The textures are computed using the selected keyframes and the camera parameters estimated by the structure from motion. A texture map is created in the form of an image using the textures extracted from the keyframes. This map is then applied to the mesh to give a realistic effect. The mesh optimization procedure takes the high-quality textured mesh and aims to reduce the number of polygons. The mesh optimization is automatically computed by selecting the number of target polygons. An optimized mesh has a lower quality than the original one, but can be efficiently used in augmented reality, virtual reality and 360 videos. The 3D model is now ready to be used for different applications. The authoring tool for the augmented reality application allows a user to start a new project. The user selects the object where the 3D model will be augmented on, for example, a magazine. The user then selects the 3D model to augment from the list of available models. The user can then select the position and pose of the 3D model to augment. The project can then be deployed on a smartphone that will visualize, in real time, the augmentation of the 3D model. The 3D model can also be used in a virtual reality application. The VR authoring tool allows the user to configure the 3D world and to visualize the 3D models available. The new acquired 3D model can be placed in the virtual world along with other previously acquired models. Interaction with 3D models can be done with a Bluetooth controller. Alternatively, it is possible to interact with a 3D model using your hands and a Leap Motion hand tracking device. The authoring tool allows the user to select the 3D model to be placed in a 360 video, for example, in the Somerset House. The user can then navigate within a 360 environment, interact with virtual objects and select the video to visualize. Once entered in the selected 360 video, the user will then find the 3D model placed in the previously selected location. Thanks for watching. More developments are on the way. Stay tuned.